Okay, so you have particular things that you want to look at? Sure. Yeah, that is going to be the free response where you have an object that moves across a potential difference, and you have to calculate the speed of that object. Let's look here. Number 2 on 2021. This one right here? No. Oh, on the free response. I don't have the free response, I don't think. Oh, wait, yeah, I do. Yeah, so it's like that one. Well, let's find one that I haven't worked, okay? Okay, yeah, so this is the spring 20, the free response. And this is somewhat like your free response. You'll have to do something like this where you're calculating the electric field. But then also number 4 will be one like you'll see too, where I'm moving across a difference in potential. And notice that I'm moving from 8 to negative 2. That means that my potential difference is going to be 10 volts. Don't worry about the signs. Signs not really important because I'm looking for the speed, not the velocity, and just don't worry about the signs. So my change in potential is 10 volts. I'm pretty sure on your exam that it's similar, or I'm moving from a positive to a negative or vice versa. So that instead of taking the difference, that is instead of saying 6, that you're going to be actually adding the magnitudes of those values together, so 10. So my delta V is 10 volts, and then I want to know, oh, and my charge, notice this is a proton, so my charge is 1.6 times 10 to the minus 19 coulombs, and my mass of the proton is 1.67 times 10 to the minus 27 kilograms. Those are on your equation sheet. If you look on your equation sheet, which you'll have a portion of that equation sheet tomorrow or Monday, the mass of the proton is right here, and the charge of a proton and an electron is right there. So those values are all given to you. So I'm going to give you these values, just this first column. That'll be on the front of your bubble form. So in that block, you'll have all those equations there, so you can look at the measure working through the test. All right, so anyway, those are given to you. And then remember that a potential is equal to a change in energy over a charge, energy per charge, so delta E over Q. So if I want to know, so my change in energy then, which is going to be 1/2 mv squared, hey Julia, is equal to Q times delta V. So now, I'm trying to get to V. However you want to do that, if you want to put in numbers, that's fine. I'm going to go ahead and solve it for V right here. So V is equal to 2Q delta V over M. I think I did that right. And then you'd put in the values here. So that's 2 times 1.6 times 10 to the minus 19. Delta V is 10. Divided by 1.67 times 10 to the minus 27, and then I take the square root of that whole thing, and then whatever that answer is, I don't know what it is right off the top of my head. Okay? Be prepared for that. In addition to that, as I said in class today, that I will also tell you what is the change in the distance that it goes through, and I'll ask you then to tell me what is the electric field. Well, the electric field is going to be V change in potential over the change in the distance. I'll give you a figure too. It'll look, I drew it in class today, but it'll look something like this, where I'll show you the electric field lines, I'll show you the equal potential lines, and I'll ask you if I have a charge that moves from here to there over a certain delta X, what is the electric field? If I know my delta V and I know my delta X, then what is my electric field? And you're just doing this. Now that is on your equation sheet, so let me just show you. On that equation sheet, it looks like this right here. Remember, there is this negative right here, but don't worry about that. That has to do with am I giving or taking away energy, but it's not really relevant here, and it won't be relevant on your exam in any way. Okay? So that's 2 questions. Yeah. Yeah, that's on there. Let me show you. Delta V is E over Q. It sort of looks a little wonky. Where is it? It's right here. I think you were the one that asked, well, how do I know if it's kinetic or potential today? Because it says potential energy right there. That was sort of what we used as we were deriving that. But on a more basic level, potential is energy per charge. You know, it's sort of like if I change it, if I take a mass and I move it up and down, that changes its potential energy. But if I move it in a horizontal direction, that changes its kinetic energy. So don't, I know you worry about that, but don't worry about that too much, okay? All right, so that's 2 of your free response questions. Are y'all okay with the vector thing too? Can we run through that? Is that okay? I know we've done it till we're blue in the face, but I'd rather y'all do it till you're blue in the face, and then that way you're really quick on doing it come Monday. So I'm just going to make up one. So it'll look something like this. Say I have 2 charges, 2 nanocoulombs minus 3 nanocoulombs. We'll say this point down here. Actually, let's, just to make this easy, let's say that this is 10 nanocoulombs. I'll try to have the numbers work out well for y'all too. Then we'll make this distance 4 meters. This distance will be what you think? 3. It's going to be a 3 meter distance. I just do that so you're not fiddling around with numbers a lot. And then I want to know what is the electric field. So I'll ask this in several phases. The first thing I'll do is just say, hey, draw the vectors and label the angle. And that'll be one question. So we'll have one vector that's in that direction and another vector that's in that direction. Find it's helpful to draw your coordinate systems like this. And then you'll need to find out what is this angle. Now let's look at our triangle right here. Let's have a triangle that's like that. And then recognize that this angle is the same as this angle. So you can get to that angle in a couple of ways. You recognize that that angle is also this angle. You'll see that. So you can find that angle. This is also theta. Or you could find this angle right here, and then you'd have to subtract it from 90 to get at that angle. Okay, so there's a little bit of geometry going on. I have to figure out what is the appropriate angle, but that's part of the problem, is to figure out what is the angle. And by the way, if I change the configuration of these, the process is still the same, but it's going to look a little bit different. So look back at some of the old tests and you'll see those. And also, by the way, in the homework, at the end of the chapter, there are some similar problems too. So let's find this angle, theta. That is this one right here. I'm looking for this angle. And so theta is the inverse tan of SOHCAHTOA, TOA, opposite over adjacent. That's 3 over 4. And that's going to be 37 degrees. So this angle then is 37 degrees. So that would be one problem. The next problem will be find the x and y components of the vectors. I always find it helpful to draw my vectors like this. So my first step will be to calculate E. I'll call this Q1, Q2. So this is E1, E2. E1 is going to be KQ over R squared, KQ1 over R squared. That's R1. So that's 9 times 10 to the 9th. Q1 is 3 times 10 to the minus 9, divided by the distance, which is 3 squared. You're going to have some nice numbers that cancel out, a lot like this, okay? Not on every problem on the test, but on the free response I have it this way. That cancels there. 10 to the 9th, 10 to the minus 9th is 1, 9 divided by 9 is 1, so this just equals to 3 newtons per coulomb. And then E2 is going to be similar, 9 times 10 to the 9th. 10 coulombs divided by 5 squared. Oh, this didn't work out so well, did it? Well, so this is 10, that leaves 2.5 down there. 9 divided by 2.5. I'm sorry, this didn't work out as well. That cancels with it times 10 to the minus 9. Whatever that is, 9 divided by 2.5. 3.6. Can I just say it's 4? I'm just going to round it up to 4, okay? Your numbers will work out more evenly. I was just making this up on the fly. So we'll call that 4. So that means that I have a 3 net Newton per Coulomb vector here, and then 4 Newton per Coulomb vector here at an angle of 37 degrees. And now I want to find the x and y components. So E1x, I'll just redraw it actually. I think that's easier. This vector is 3. And then I have 2 components. I have 4 cosine of 37 and 4 sine of 37. That's 3.2. It's 2.4. Okay, so those are my x and y components. And then the next step would be to find what are the sum of those x and y components. So I would add up the electric field in the x direction and add up the electric field in the y direction. This is just going to be 3.2. This will be 3 minus 2.4. And so I get 3.2 in this direction and 0.6 in this direction. And then the final question is, what is the magnitude? And then I think there's a separate question that asks, what is the direction? So what is the magnitude? I'm looking for the magnitude of this vector. Look, I can move that. No. I can redraw this vector over here. This is my 0.6 vector. So the magnitude of my vector is equal to, that's what that means. The arrow means it's a vector, E means it's the electric field, and the parallel bars means it's the magnitude. That's going to be the square root of 3.2 squared plus 0.6 squared. That's probably about 3.3. I don't know exactly what it is. And then I want to figure out what is this angle. That angle theta is the inverse tan of 0.6 over 3.2. And that's 11 degrees. I always need to qualify my angle. That would be 11 degrees from the plus x, or 11 degrees above the plus x. Beware that if I'm dealing with a vector that's in some other quadrant, like right here, for example, there are 2 ways. Let's say that this is 30 degrees. I could say 30 degrees below the negative x. Or I could say 210 degrees from the plus x. Either of those would be correct. I think in the problem I do say to measure the angle from the positive x-axis, but I will take either one of these, for example. Not in the first quadrant, is what I'm saying. I forget which it is in, but not in the first. Elena?
I always get confused when we're doing the angles, like when to use the 3 and the 4 as the size, or when to use the new vector components as your size.
Ah, yes, I see. So, good. You're going to have to do both, because there are 2 angles that you're finding, right? When you're finding this angle, you use the coordinates of your charges. Okay, so that I'm just trying to figure out what is the angle of my electric field vector right here, E2. So in that case, the first thing is you're going to have to use the 3 and the 4. But down here, right here, I'm looking for the angle of the resultant vector. And in that case, I'm using the magnitudes of my x and y components. And that's where you're using the point, in this case, the 0.6 and the 3.2. So it depends on, I think probably the best thing to do is to draw your triangle every time. See, in this case, I was working with a triangle with 0.6, 3.2, and then I was looking for this angle. But up here, I was working with a triangle that was 4, 3, and I was looking for this angle. You see how those are different? That I'm working with different triangles. It's still a little confusing, isn't it? In practice, though, I mean, you're always going to be using the 3, 4, because I always give you a 3, 4, 5 triangle. You're always going to be doing that first, and then later in the problem, towards the end, you're using the components of your electric field vector, these x and y components that we found, 3.2 and 0.6, in order to find the angle of your new vector. The old vector and the new vector. Can you expand just a little bit?
The 3, 4 triangle, that would be the vector that you're given, and then the resultant one would be the vector that you found after.
Sort of, but the 3, 4, these are not components of a vector. These are coordinates of our charges. So I'm just doing that to figure out where are the charges in space, to figure out that angle. Those aren't vectors, the 3 and the 4. Those are coordinates, right? Distances between the charges. So I'm just doing that to figure out what is my angle of my electric field vector with respect to the x-axis. But down here, I'm doing the same thing mathematically, but it's physically a different thing. That I actually have two electric field vectors or force vectors that are causing this new resultant vector. Remember, resultant just means the sum of all the vectors. So we've done this a lot. Like we did this last semester, and this is the last time that we're going to do it for the entire life until you take the MCAT, and then you'll need to review all this. But so it's my last chance to get you on, not to get you, to see that you know how to do 2D vectors. That's really why I'm doing this. The electric fields or the forces are important. It will be an electric field problem, by the way. But it's really, I want to make sure that you do this mathematically. There is, by the way, another part to this problem at the very end of it, don't miss it, where I ask you, okay, now what is the voltage, or what is the potential of this? Let's just do this right quick. Eraser. What is the voltage or the potential at this point? That's relatively easy. It's the sum of the individual potentials, which is going to be V1 plus V2. That's going to be KQ over R, or 9 times 10 to the 9th. Q1, negative 3 times 10 to the minus 9, divided by R, which is 3, plus 9 times 10 to the 9th. Q2, 10 times 10 to the minus 9, divided by R, which is 5. A couple of things to note here. The negative sign, I keep. So if I have a negative charge, which you probably will, you will keep that negative sign. Anytime you're dealing with scalar quantities, which voltage is a scalar quantity, then you keep that negative sign. And then also recognize that the equation has changed a little bit. There's no squared right there. So that's, again, I get some nice cancellations that make it easy. So this is negative 9 plus, that cancels, that gives me a 2, plus 18. 18 minus 9 is equal to 9 volts. Like a battery, 9 volts. Okay? So that's just one part of that last problem. I think there are 5 parts to that first question. So spend 10, 12 minutes on that first question, typically a couple of minutes per question. So 10 or 12 minutes on that very first multi-part question, and then you'll do the others that I've shown you. Okay? 100% on this one. You get 100%. Can we talk a little bit about these other questions? Like, no, you might have specific questions, but.
So when we did in class, number 5 on 2020, I still don't really understand.
Was that one where is the electric field or the force equal to 0?
Yeah.
Yeah, that's what I'm looking for. So, but that comes up several times on the exam, so I want to make sure that we're good on that. Yeah. All those are really similar, so let's try to find a good hard one. All right, let's look at number 14. This is number 14 on 2016. We've done some that are similar to these. I mean, all the problems are similar. They are. They're all covering the same material. In fact, I have a little spreadsheet that says, okay, I want 2 problems covering this topic and 3 problems covering this topic, and that's why all the exams look similar, because, they're covering the same material, but they all look different, too. So if you're not comfortable with the material, then you're probably gonna say, well, those are completely different, when in fact they're actually quite alike. All right, so let's look at number 14. Consider this configuration of charges. At what point is the electric field equal to 0? So, as I said in class, nice thing is to first look at the parts where the electric field cannot be 0. Let's just start with A. That's probably a good place to start. I'm going to draw my electric field. I'll let this be red and let this be blue. So, the electric field due to the plus 2q charge is in that direction. It's a small charge, but I'm relatively close to it. The electric field due to the 4q charge is going to be quite a bit smaller. I know that it's smaller, by the way, even though this charge is twice the charge of this charge, it is 4 times the distance away. So remember, electric field is kq over r squared. So it's twice the charge, but it's 4 times the distance. That means it's 1/8 the electric field at that point. Okay, y'all see that? Twice the charge, but 4 times the distance away. So, I can't even draw 1/8 of that vector. But, also, both vectors are in the same direction, so it doesn't really matter how big they are with respect to one another. I'm never going to get a 0 electric field there. You follow? Because they're both in the same direction. Similarly, over here at E, I'm going to get a really big electric field due to that big charge, which is really close, and a tiny little electric field due to the small charge that's far away. So that's not going to work for me. That's never going to give me an electric field equal to 0. Over here in the middle, if I'm close to this charge, I'm going to get a really big electric field due to that big charge, and then a smaller electric field due to the small charge. So that's never going to go to 0, right? Because I got a big vector and a small vector. They're never going to cancel out. I'm just going to erase that. Let's look at B. If I'm looking at B, then I'm going to get a vector in that direction due to the big charge, but I'm far away from it, so it's minimized. And here, I'm going to get an equal-sized vector. I'm closer to the small charge and farther away from the big charge, so the electric fields then will be equal to one another.
And if it was the same magnitude, it would be
Yeah, so if this was 2q instead of 4q, you're right, C would be the answer, because then I would have equal and opposite vectors that would oppose one another and cancel them out. That's difficult to think through. Like, there are lots of things that are going on inside my head as I'm thinking about that, because I'm thinking about how does the value of Q interplay with the value of R to cause an electric field that will be equal but opposite. So you need to really practice with that, because it comes up on, gosh, 2 or 3 or maybe even 4 questions in various ways, because it comes up when we're talking about forces and electric fields and potential too. So it's kind of important that you be able to do that. And I think that's probably why I say that this exam is the hardest exam. It's the 2D vectors, because some of you just haven't mastered 2D vectors. I think y'all have, right? You mastered 2D vectors? That needs to be yes by Monday. But also this is quite difficult to think through. There's lots of moving parts to it. Take each point and ask yourself, okay, what are the vectors here? All right. Let's look at another one, because y'all are giving me blank stares. And then we can open up to other questions. Okay, let's look at this one, 6. You had asked about this one, I think. This one's similar. I have a net force on these charges, and I want to know in which quadrant does the resultant vector lie. So you want to draw the, oh wait, no, so look, I have a nice little easy one here, because I have an attractive force between those two charges, between the plus 5Q and the minus Q, and then due to this charge, I have a repulsive force that's of equal magnitude. Because the two charges, they're of different signs, but the two pairs of charges have the same magnitude. That is a 5Q and a Q. So those two are going to be equal vectors in the same direction. And then these two vectors are going to be equal and opposite. They're both attractive. So these two will cancel out, and so my resultant vector then will be in quadrant 2. I'm pretty sure I gave you a quadrant problem. I don't remember exactly. I'm pretty sure that I did. So that's what you do. You draw the vectors, but it's important that you draw them relatively correct to one another. That is, that you're drawing them the right sizes, bigger and smaller is correct. That's true for those questions which you're going to have where, let's go back up, I think on some of the newer exams I have those. We've worked some of them. But like number 1 here, I think we worked this in the workbook. Number 1, where I have these charges that are, this is 21, spring 21. I have these 3 charges, and I want to know what is the vector that best represents the force. Just draw your vectors. So I have one vector that goes in this direction, and then I'll have another vector that's attractive to the minus 2Q, but it's going to be half the size. Oh, no, a quarter the size of that other vector. I know that because F is KQQ over R squared. The two Q's remain the same. They're both 2Q, but the distance is doubled, so that means that my force is quartered. So this force, if this force is F, this force is 1/4 of that value, which means that D is the right answer. So you'll have one like that too. Not pretty sure, I'm confident that you will have one like that.
If the negative 2 was negative 4 though, would it be the same? They would both cancel, like it would be C?
No, it couldn't be negative. Oh yeah, if it was negative 4, it would be C. Well, that would be less obvious. I wouldn't give you one like that. But if it was negative 4, it would be, then this force would be half F. But that becomes less obvious. Is it C or D? So, but yeah, I wouldn't give you that question, but yeah, the answer would be C. I will make it more obvious to you, okay? Okay, good. You're going to have an electric field question. I'm pretty sure I gave you one both multiple choice and free response, what is the sign of Q3? If you get one of these, I'm pretty sure there's one of these. If Q1 has a magnitude of 2 coulombs, you know it has to be positive because there are the field lines coming out of that charge. And then I want to know what is Q3. Well, first of all, notice that Q3 has to be positive because the field lines are coming out. So those go away. Q3 also has to be bigger than 2 because there are more field lines coming out of Q3 than there are coming out of Q1. And then see here that how I have 2 field lines coming out of a 2 coulomb charge. So I can say in my mind, well, one line is equivalent or gives me 1 coulomb of charge. So that makes it kind of easy here. So that means that Q3 has to be 6 coulombs. By the way, what's Q2? -4. It has to be -4 coulombs. This is +6, and that's -4. Alrighty? You'll see one of those on free response. You have to draw the field and equal potential lines. And then I'm pretty sure there's a multiple choice. There usually is on all the exams. So if there's a problem that repeats exam to exam, that's usually one that I consider pretty important. And you're probably going to see it again on Monday. All right, particular questions. I'm sort of popcorning around.
Number 6 on the spring 19.
Of course. Okay, yeah, so this one with the electric fields? Yeah, so if Q1 has a magnitude of 10 coulombs, what is the charge of Q2? So this is one that's a little bit harder. So, first of all, I know that Q2 has to be positive or negative. Positive. So, no, I'm sorry, negative. It has to be negative. If it was positive, it'd be easy, right? I would know the answer right off. So, do that whenever you're doing multiple choice tests. Go through the options and see which one is correct or not correct. Because often, especially on my test, that I pick those for a particular reason so that you'll be able to rule out certain ones. Also, Q2 will have a bigger or smaller charge than Q1. Well, it has to be bigger, right? There are more lines. So it has to be negative and bigger than 10 coulombs. Oh gosh, I know the answer now, right? Because I know it can't be this, and I know it can't be that, so D has to be the right answer. So this goes from being sort of a slightly difficult problem to a relatively easy problem. But let's show how we can get the charge for Q2 exactly. Because I know that the ratio of these two charges has to be 3 to 5. Because there are 3 lines over here and 5 lines over here. So if Q1 is 10 coulombs, then I know that, well, really, it's easier to say that the ratio is 5 to 3. You follow what I'm saying that? So 10 times 5 to 3 will give me the charge. The ratio has to be 5 to 3. Hold on, no, a better way, maybe we'll say it this way. That Q1 over Q2 has to equal to a ratio of 3 over 5. So then I know Q1, that's 10 over Q2 is equal to 3 over 5. So Q2 is equal to 10 times 5/3. That's 50 over 3, or 17, minus 17. So, that's kind of a difficult problem. Students often don't really work with ratios very well in that way. But I made it really simple by, if you go through and rule out the ones that are obviously not right, then you'll be able to get to the right answer. And as I said, often that's the case. You might not be able to get down to one option, but you can usually get down to 2, maybe 3, but usually 2. And then, 50%. You're guessing 50%. That's pretty good odds. All right. Yeah, so if remember, field lines go out of positive charges and they go in to negative charges. I imagine that there is a positive test charge in the vicinity of my charge, and whatever force that positive test charge feels is also the direction of the electric field. So my positive test charge feels a repulsive force. Over here, my positive test charge feels an attractive force, so the electric field goes into the charge. Out of positive charges into negative charges. But if you forget, just pull out your positive test charge, and then you can figure out what is the direction of that field by asking what is the direction of the force. There'll be some questions sort of like these about insulators, conductors, charging, maybe something like this. Oh, this one was easy, right? Do I do this one? This one's easy. Let's just do it right quick. So my electric field, due to this charge, is in that direction. Due to this charge is in that direction. Due to this charge is in that direction. And due to this charge is in that direction. But they're all the same, so it's going to be 0. Hey, Sam? All right. Okay, the units for our various things. Okay, so just potential. Well, no, electric field, the units for it, I think, are probably more confusing because the units, remember, electric potential is defined as a force per charge. So usually we do newtons per coulomb per potential, but also we see that potential can be defined in volts per meter. If you forget that, remember that the electric field is equal to delta V over delta X. So the units for electric field can be in volts per meter. I might ask you that too. Or electric, yeah, no, never mind. That's all I wanted to say about that.
That's good job. I didn't know how it could be volts. V over energy also.
Yeah, they're just the same units. You know, they really are. That's going to be, well, they have the same basic SI units. That's kilogram meters per second squared coulombs. These are both equal to newtons per coulomb and equal to volts per meter. It's just they're expressed in a different way. I mean, if you run into electric fields out in the world, usually it's expressed in this way. But I like to keep the newtons per coulomb to remind us that electric field is really just a force. It's describing a force field, a field of forces.
Would it be wise to study it on like the different conversions, like the difference into the like -9 into the
Yeah, if you're not familiar with them, let's remember them right now, especially nano. I mean, I think nano is probably the biggest. Nano coulombs is equal to 10 to the minus 9 coulombs. I'm trying to remember if I had any micro. I don't think I did, but you know, is nano micro milli? 10 to the minus 9, minus 6, minus 3. That are the big ones. Or the small ones, actually. Those are the small ones. Always remember minus 9. Nano is minus 9 because nano and 9, they're just a couple vowels away from one another. Micro, I don't know, I just remember that's minus 6. Milli, micro, nano. Milli, micro, nano. Yes, but you definitely need to know this. Definitely need to know nano. Yeah, sure. There are those things. Mnemonic.
well, that's the thing maybe for cat safe copies, so I'd say never make maybe clean copies not yet.
Yeah, that's going to be real helpful for everybody else. Thanks.
I mean, I don't think I would get it, but you can come up with something.
Yeah, so that gets your centi in there. What was the last part?
Messy gas.
Messy gas. Oh yeah, that gets your mega and your giga. We won't use that till we get to light. Okay? What else, folks? So if you encounter a problem like this, it's probably easier than you think. I'm looking for the magnitude of the force on the 2 nanocoulomb charge. It looks complicated because there's 4 charges, but when I start drawing the vectors, I'll quickly see that it's not that hard. That these 2 vectors, which are attractive because the 2 charges are identical, that those 2 vectors just go away. They cancel out. So I don't even really need to think about these 2 nanocoulomb charges. So then it becomes a relatively easy problem where I have the force between 2 charges. I know that force is going to be repulsive, and it's just 9 times 10 to the 9th, 2 times 10 to the minus 9, 5 times 10 to the minus 9, divided by the distance 3 squared. That was a minus 9 right there. So it's 10 times 10 to the minus 9, or 1 times 10 to the minus 8. So if you encounter a problem that looks like it's really complicated, it's probably not. That's usually true with my tests, that if it looks really complicated, if you understand those basic principles, and there aren't that many, forces, fields, and potential, if you understand those 3 basic ideas, there are some offshoots, of course, and you need to know how to manipulate the equations. But if you understand those basic principles, then most of the questions are going to be fairly straightforward applications of those. But I know that's easy for me to say because I've seen those things for a lot of years, and they're new to y'all. And I remember when I first saw them, they were like Greek to me, But with practice, you too can understand fields, forces, and potential. All right, go ahead. Okay, yeah, we worked one like this. So this is where those kinematics equations come into play, or you might need them. Several parts to this. The first thing that you need to do, I'll label those parts. First, find the force. Second, find the acceleration. And then third, apply the kinematics that's appropriate to that question. So 3 parts. F is equal to QE. A is equal to F over M, and then apply the kinematics equations. So F equals QE first. F equals 220 newtons per coulomb times Q. Oh, this is a proton, so that's 1.6 times 10 to the minus 19 coulombs. That's 3.5 times 10 to the minus 17 newtons. So that's my force. B, the acceleration is F over M. So I just divide that by the mass of my proton. If you don't use the EE button, make sure that division gets put in parentheses, okay? Otherwise, your order of operations will be all off. Let's say the mass, right? I'm putting in the charge. I get 2.1 times 10 to the minus 10. That's in meters per second squared. And then finally, I want to know what is the velocity. I know that V is equal to A times T. That's one of my 2 kinematics equations. V equals AT. X equals 1/2 AT squared. It's from last semester. So that acceleration times the time. 1 times 10 to the minus 6. I get 21,000. C is the right answer, meters per second. Okay? I know there's several parts to that, and there are several places to make mistakes. Be careful with your calculator, your order of operations. Okay? I don't remember if I put a question like that, but I often do. I really don't remember. Not playing coy, I just don't remember. Okay? Remember, as I told you in class, be careful that if you see a capacitor question, don't stop there if you're practicing old exams, to keep looking, because sometimes if capacitors made it into the exam, I embedded them sort of central just to get more questions on a page. So just look to make sure there aren't any more potential questions. If you have any questions about, is a question going to be on the exam, or like, is this material on the exam, you can shoot me an email over the weekend. I'll check my email every few hours or so and respond in a timely way. But not on Sunday night after 8, bedtime for Chad. 8. After 8 on Sunday night, not answering your email. In fact, my phone just goes off. It goes to do not disturb at 8. So I don't even get anything at 8 o'clock. Yeah. Yeah, they do. That's okay. They can. That's why I give them my